Hello guys, welcome to the mathematics lesson. This is the mathematics lesson 10. In today's lesson, we'll be looking at the approximation. Alright, so what is approximation? So we are saying approximation is the way of reporting measured quantities to the nearest unit. So you realize that in this world, we do measurement of things like maybe the building, how tall it is, how wide is the room, how long is the room. So most of the measurements that are done are actually not very accurate, but are usually reported to the nearest unit. So approximation is actually a way of reporting measured quantities to the nearest unit. So let's say we want to draw a line of length 10 centimeters. So we want to draw a line of length 10 centimeters. If we drew such a line, in reality, its measurement cannot be exactly 10 centimeters. So whatever measurement that we do in reality, it's never 100% correct or accurate. So that's what we are saying. If we are we try to draw a line of 10 centimeter long, if we were to draw it, it won't be exactly 10 centimeters. So this line, if it is the one we want to draw, and we assume that it is 10 centimeters, in reality, it won't be 10 centimeters. So we are saying the measurement can be expected to be closer to 10 centimeters by 1 centimeters or away from 10 centimeters by 1 centimeters. So what I'm saying is this, that the measurement that we can draw of this line can be expected to be closer to 10 centimeters by 1 centimeter or away from 10 centimeter by 1 centimeter. So every measurement that is done actually is expected to be closer or away from the actual measurement, and that number by which it is expected to be closer or away from the actual measurement, that number is determined by the instrument's least unit of measurement. So for instance, if you were to measure this length of 10 centimeters, you would use a ruler that got the marks on it, centimeters. So it will have the smallest unit of measurement as 1 centimeter, because we would move from 1 centimeter, 0, 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeter, 5 centimeter, 6 centimeter, 7 centimeter, 8 centimeter, 9 centimeter, then 10 centimeters. So the difference between each unit is 1 centimeter, and that is how much one can be correct to the actual measurement, or that's how one can be wrong away from the correct measurement, by that unity difference between the consecutive units. For example, 1, 2, 3, 4. There's a difference of 1 centimeters between those centimeters that we are counting until we reach 10. So according to standards of making an error, a person is allowed to make that error of 1 centimeter, especially if they are measuring a length of 10 centimeters. They're expected to make an allowed error of 1 centimeter away from the actual or above from the actual. So that is, if they were to be away by 1, maybe they can be at 11, or if they were to be maybe closer, maybe 9 centimeters. That way, that kind of error is actually allowed. All right, so that's what this measurement can be expected if a person measures or draws a line of length 10 centimeters in reality, then they are drawing, if they think they have made it to 10 centimeters, then that value cannot really be believed, but it can be believed to be either closer to the actual 10 centimeters by 1 or away from the actual 10 centimeters by 1 again centimeters. All right, or 1 centimeter. So we are saying this is because a measurement can only be correct or wrong by the least unit of measurement of the instrument. So by standard, mathematicians and scientists think that the person making a measurement, their results can be affected also by the instrument they are using to measure. So they can be wrong by 1 unit of that instrument, least unit of the instrument, like I said in this ruler, for example, which is measuring in centimeters, trying to measure 10 centimeters. There is actually 1 centimeter difference, a difference between units from 1 to 2, 1 centimeter, 2 centimeter. Between these, there's 1 difference. 2, 3, 4, 5, 6. You see, these numbers I'm counting, the neighboring numbers, they differ from each other by just 1. All right, so that is what a person doing measurement with that instrument is expected to make an error with, even when themselves they think they've made the accurate measurement, but their measurement cannot be accepted as very accurate because they'll think there are errors introduced by a human being or the apparatus itself based on the least unit of measurement of the instrument. So we are saying when we have the least unit, for instance, if we are using a 10 centimeter rule to measure this 10 centimeter, so we are saying the least unit of measurement here can be 1 centimeter, 1 centimeter mentioned here. And then we are saying if we have the least unit, we have this 1 centimeter, we obtain the value called the absolute error. So if we get 1, we have it 1/2, which will give us 0.5. That value will be the absolute error. So we are saying that, for example, the absolute error of the measurement of the line should be of that line of 1 centimeter, least unit of that instrument. If you get that least instrument of the least unit of the instrument, divide it by 1 or half it. So to half it is to get 1/2 as half, multiplied by that least unit. Then we are going to get 0.5 centimeters. And this 0.5 centimeters is called absolute error. All right, so we are saying if we have a measured value plus, like which measured value here, whatever measured value we have made, plus absolute error. So the measured value that we have made on an instrument plus an absolute error like this one here gives us what we call the upper limit of the measurement. Then similarly, if we have the measured value minus the absolute error, gives us what we call the lower limit of the measurement. So basically what is being said here is that that line, if we drew it, the value that we are going to get is called the measured value. The value that we are going to expect that our line is called the measured value. So we would think we are measuring 10 centimeters by drawing that line. So we will get that 10, for instance. If we get that 10, then plus this absolute error, then now we get what we call upper limit of the measurement, meaning the value by which we can be aware from the actual value. The allowed error by which we can be away from the actual value. That is what is being called here as the upper limit of the measurement. Then also if we get the measured value minus absolute error, then we get what we call the lower limit of the measurement. And the lower limit of the measurement is the value that is expected to be lesser than the actual measurement. The lesser, so the allowed value expected to be lesser than the actual measurement. So all this is what is done in approximation. It is used by engineers, mathematicians, and the scientists. So whenever they are measuring scientists, whatever they are measuring, they will always consider it to have an error of what we call absolute error, and then they would be able to determine what they call the upper limit of the error in that measurement, and then there will be also the lower limit of the measurement. All right, so what we are saying here is that in the drawing of the line of length 10 centimeters, so in that drawing of the line 10 centimeters, we can say the upper limit of the measurement. So the upper limit of the measurement, meaning the expected error that someone should be away from the actual value 10, should be upper limit of the measurement, is going to be equal to, we are saying the measured value plus the absolute error. So in this case, the measured value that a person thinks they have measured is 10 centimeters, then plus the absolute value is 0.5 centimeters. Then when they add these, they'll get 10.5 centimeters. So 10.5 centimeters becomes the value they are expected to go beyond, by which they can go beyond the actual value. And if they were to go beyond by the actual value by this, then that error is actually allowed. All right. Then we are saying lower limit of the measurement also is given by the same measured value minus absolute error. Let's move up. So we are saying which will be equal to the measured value is still 10, then minus the absolute is still 0.5. Then when we subtract, we get 9.5 centimeters. So 9.5 centimeters is the lowest value they expected to make as far as an error is concerned in getting this 10. So the value by which they can be away, the lower value by which they can be away from the actual value in the approximation is expected to be 9.5 centimeters. All right, so we are saying, therefore, the correct approximation for the drawing of the line of length 10 centimeters should lie between 9.5 centimeters and 10.5 centimeters, correct to the nearest centimeters. So if you were to make that line, then and tell us that it is actually correct, but then we'll say you won't be managed to be able to get exact return even when you claim to get it. But we are saying if you are to get it closer to 10, your value must be in between 9.5 centimeters and 10.5 centimeters, because these are very close to 10 centimeters. All right, so you're saying that we can report such a measurement as, so if we were to make measurement of that 10 centimeters, so we expect it to be above by 10 by 0.5 centimeters. So we report such a measurement as 10 plus or minus 0.5 centimeters, or we can report it in this way, which is we can create an equality, which means our value lies between, it's either equal to 9.5 centimeters or greater than 9.5 centimeters, and then it is expected to be less than 10.5 centimeters. So that's how such a number is supposed to be reported. Now, however, all what we are learning here is a theoretical, how values can be found theoretically. All right, so what we are saying here is that upper limit is also called the upper bound. So in your solving maybe past papers or whatever it is, or other books, you may find that they're calling the upper limit as the upper bound, while the lower limit is called the lower bound. So let's look at example 1 and see how this comes either in exams or books, how they ask questions. So we have this question here which says, find the absolute error, upper limit and lower limit of 39 meters. So in answering this, first of all, we need to do what? To determine the least unit. So if we are measuring in 39 meters, so we expect the difference between 38 and 39 to be actually 1 meter. So that one becomes the least unit of the measurement. So we are going to say the least unit is actually 1 meter of that apparatus that is going to measure this. Then now we can calculate the absolute error. So we're saying absolute error now can be equal to half of this. So 1/2, which means half of this 1 meter, which will give us equals 0.5 meters. So we have now found the absolute error. So they said find absolute error, upper limit and lower limit of 39. So this will be the absolute error. Now the upper limit will be equal to the actual value or the measured value minus or plus the absolute error, this one, which will be equal to 39 meters plus then absolute error, which will be 0.5 meters. When we add 39 plus 0.5, 39 plus 0.5 will get 39.5 meters. So this one is the error that is expected to be, by which someone can move away from 39. The highest they can move away and they still be considered to be closer to 39. Then the lower limit can be equal to, we are saying measured value, then minus the absolute error, which will be equal to, the measured value is still 39 meters, then minus, then the absolute error is still 0.5. Then let's move, and we subtract 39 meters minus 0.5 meters, we get 38.5 meters. So this one again is now the lower limit. So the value by which someone trying to find 39 is expected to be below, for them to be closer to 39 meters. So the lowest value they can be at for them to be closer to 39 meters, and this is the allowed error they're supposed to get for them to be closer to 39 meters. All right, so let's look at example 2. So example 2 says, number 1, find the error in each of the following dimension, where we have A 340 meters to the nearest 10 meters, then B we have 4.56 centimeters to the nearest centimeter, then C we have 15 kilogram to the nearest kilogram. Then number 2, a dimension is stated as 4.3 centimeters plus or minus 0.05 centimeters. Find A, the lowest bound of the dimension, then B, the upper bound of the dimension. Then we have 3, they're saying the length and breadth of a rectangle to the nearest centimeter are given as 15 centimeters and 10 centimeters respectively. Then they're saying find A, the shortest possible length and the shortest possible breadth, then B, the longest possible length and the longest possible breadth, and then C, the limits between which the areas must lie. All right, so let's start with A here. So we'll say solution for A. So for A, they're saying we should find the area in each of the following dimension. In A, 340 meters to the nearest 10 meters. So when they say to the nearest 10 meters, then they're telling you that the least unit of measurement is actually 10 meters in such a measurement. So we're saying to say the least unit is 10 meters. Then the absolute area now is going to be equal to, then we'll get half of 10 meters, which we'll say is equal to 5 meters. So that will be the absolute area. So let's move to B. So B, we have 4.56 centimeter to the nearest centimeter. So in this case, when they say to the nearest centimeter, so such an instrument has got a decimal places, decimal numbers here. So how many decimal places are these numbers occupying? It's 2, 1, 2. So meaning the instrument that can measure this must have the least unit of 0.01. So 0.01. So it is able to capture, if it were to start from the beginning, it can be 0.01, 0.02, 0.03, 0.04, 05, 06, 07, 08, 09. Then it can move now to 1 centimeter. Then again it starts 1.1 centimeter, 1.2 centimeter, 1.3 centimeter, 1.0 centimeter. So yeah, so like that, we'll be able to tell that the least unit here is actually 0.01. So we are saying the least unit is 0.01 centimeters. Then we'll be able to find the absolute area equals half times this 0.01 centimeters, which will give us 0.005 centimeters. All right. So let's see. C. Yeah, sorry, this is C. So C, we have the least unit is actually 1 kg, because we have 15 kg then to the nearest kg. So since we don't have a decimal, meaning we are moving whole numbers, so we have, if we start at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 kg. So meaning between the difference of the units, we have actually 1 kg difference, meaning that would be the least unit of an instrument measuring this 15 kg. So being 1 kg as the least unit, then the absolute area would be equal to half of 1 kilogram, which would be 0.5 kilogram as the absolute area. So let's answer 2. So question 2 said a dimension is stated as 4.3 centimeters plus minus 0.05 centimeters. Then find the lowest, the lower bound of the dimension. Okay, so let's start with A. So now what they want is to find the lower bound. So we know the formula that the lower bound is equal to the measured value, then minus the the absolute error. So now, in reporting, the measured value is always in front, as you saw just recently. Then this one here is called the absolute error. So if you are reporting the lower bound, you get this one, you say equals 4.3 centimeters. Then instead of getting plus, you get minus. Then you subtract 0.05 centimeters. Then you get 4.25 centimeters as the lower bound of this. So then we'll get the upper bound, which will be equal to the measured value, then it will be plus absolute error. So get the same equals, so we'll get 4.3 centimeters. Now we use plus, then we'll get the same 0.05 centimeters. Then we'll say, we'll add this, then we'll get 4.35 centimeters as the upper bound. So this, the value now lies between 4.25 and 4.35, which now was reported like that. All right, so now let's look at the example 3. Example 3 says the length and breadth of a rectangle to the nearest centimeter are given as 15 centimeters and 10 centimeters respectively. So if they mention respectively like this, and then here they've told you that this length and the breadth of a rectangle to the nearest are given as 15 and 10 centimeters respectively, meaning 15 is for length and then 10 centimeters is for the breadth. Then they're saying we find the shortest possible length and the shortest possible breadth. So now we'll get the length here and find the error there. So first of all, say n. So first, let's find the least unit for 15 centimeters. So the least unit for 15 centimeters would be actually 1 centimeter. So the least unit would be 1 centimeters. Then the absolute error of 1 centimeter would be equal to 1 over 2 times 1 centimeter is equal to 0.5 centimeters. That would be the absolute error. Then now we would want to find now the shortest possible length. So here now, if they are saying the shortest possible length, it is as good as saying the lower limit or the lower bound of length, the lowest they can go for the length in terms of measurement for them to be closer to 15. So now you use this one. So you say the shortest possible length, you use the upper limit formula. So will be going to be equal to, then you get the measured value, then minus, then you get the absolute error here. So you say equals the measured value will be 15 itself, then minus an absolute error which will be 0.5 centimeters. When you subtract, you get 14.5 centimeters. So this will be the lowest possible length that will be gotten, which will be closer to 15 in the lowest. Then now we get the lowest or the shortest possible breadth. So then it also going to be equal to this breadth here. Then we'll say 10 centimeters, say minus the same 0.5, which will give us 9.5 centimeters. So then we'll also go to C. There's no space here. Let's move now to C. So to B. So the longest possible length and the longest possible breadth. So now they've moved it to lower limit. Now they've gone to the upper limit, or the longest possible length and the longest possible breadth. So the same formula holds. The least unit is still 1 centimeter. then the absolute error is still 0.5 centimeters because we are dealing with the length whose longest possible length we are trying to find. So we already determined the least here. Even for this one, it will be 1. So now we'll say the longest possible length is going to be equal to, then we'll get the measured value, then it will be plus now the absolute value, error then which is going to be 15 plus then 0.5 centimeters, which will give us 15.5 centimeters as the longest possible length. Then we'll also get the the longest possible breadth. We'll use this one now for breadth, where we'll say equals then 10, then plus 0.5 centimeters, which will give us 10.5 centimeters. So we have found B. Now let's go for C, where they're saying we find the limits between which the area must lie. So here we need to find the area using the lowest possible, the shortest possible length, and then the shortest possible breadth. Then also we'll get again the area for the longest possible length and then the longest possible breadth. Then we'll be able to come up with a way of reporting such a value for us to have what we are saying, the least, or to know where the area is going to lie. So here we'll say equals largest possible area. So we will deal first with the largest possible area is going to be, we'll deal with the longest possible length here times then the longest possible breadth here, because remember area must be given by length times breadth. Now because in measurement there will be that error in measurement, so we'll begin with the longest possible length that a person can go beyond, but they can be still closer to 15, and then the longest possible breadth by which they can be away from 10 centimeters but still closer to 10 centimeters. So we will bring this one, so we get 15.5 times now 10.5. Then when we multiply we get 162.75 centimeters square or square centimeters. Then this will be done. Then now we'll go for the other part, which will be the smallest possible area. So use the smallest possible length times the smallest possible breadth, or the shortest possible length times the shortest possible breadth. Then the values we got already here we got 14.5 centimeters times here we got 9.5. When we multiply we get 137.75 centimeters. So now since the question is saying the limits between which the area must lie, so we can report it in this way. We can say we can have 137.75 centimeters, the lowest area, which is less than or equal to area. So the area will score this lowest, which will be 139.75 square centimeters. I had to put what is here now, so here I have to put the square, not what is there. So here I have to put the square, equally here the square. Okay, so the lowest possible area would be 137.75 and the highest can be, again here I should have put something like this, good, greater than. So that's where the area can lie. Between the lowest should be 137.75 square centimeters, and then the highest can be 162.75 square centimeters. So let's look at what we call absolute error. We already talked about absolute error. So we're saying the absolute error is the difference, or is also the difference between the actual value and the measured value. So absolute error now can also be represented in another form, where we are saying the difference between the actual value and the measured value. So in this case, we are saying, let's say in our measurement of the 10 centimeter lines, in our measurement we are allowed to get, in the measurement of 10 centimeters, the upper value we can get away from this one is 10.5 centimeters, as you saw earlier on. So this one is called the actual value, and then this one is called the measured value. So now the difference between the measured value and the actual value will give you what? The absolute error still. So this is another way of showing it. So for instance, if we say that 10.5 minus 10, we'll get what? 0.5. This is what we got even at the beginning when we said if we were to measure 10, we said 10 centimeters, the least unit of that instrument that would measure 10 centimeters should be 1 centimeter. Then we said for us to get absolute error, we get 1 centimeter divided by 2, which would be what? 0.5. So we are still getting 0.5. So this is another concept in which absolute error is represented. So absolute error is represented in another concept where you get the measured value, because maybe you measured 10.5, you didn't get exactly the 10 centimeters because you are not expected to get exactly the 10 centimeters. So you can be away either by 10.5, or you can be away by or you can be closer to 10 by 9.5. So that's how it can be. So you can either be away or you can be closer. So if you are closer by 9.5, so you can still say 9.5 minus then 10, which will be the actual, which is equal to negative 0.5. So now you understand a bit here. So we are saying the absolute error is the difference between the actual value and the measured value, which can be equal to measured value minus actual value. Then we put it in modulus. So these bars are called the modulus, meaning the value which must come out of this modulus must be positive always. That's why I told you that you understand a little bit soon. That's why I said if for instance we say 10.5 minus actual 10 will get 0.5. So we are saying the upper 10 here minus the actual value 10 will give us an absolute error of 0.5. Now, if we get the lower value that we can get 9.5 centimeters minus the actual value, which will be 10, then we'll get 0.5 centimeters negative. So If this one value is inside here, you shouldn't report it as negative, because these bars here, they'll make it change into positive. So whether you are subtracting a smaller one or a bigger one, it will still come out as a positive. So this is also another way of finding the absolute error in a measurement. Now where now a person has done the actual measurement. After they have done the actual measurement, now they're expected now compare that measurement they have done with the true value. If the measurement they did was this, then the true value they're supposed to get, which they can never get to 100% because it's hard. Maybe the true value is 10 centimeters. Then the difference between the measured value, this one, and the actual value they're supposed to get will give us the absolute error. So absolute error, the way we found it at the beginning and the way we are finding it here is actually the same. The difference is that at the beginning, we are talking about how you can do it theoretically, where you tell a person to say measure 10 centimeters. Then theoretically, you'll be able to know that the approximate value they should get for them to get closer to 10 should be 10.5 or 9.5. And how are we getting this? We are saying, if you look at this 10 they are trying to measure, the least unit on that instrument will be 1 centimeters. Then we said if you have this one, you get what? If you have this one, you get 0.5. 0.5 centimeters. If you get 0.5 centimeters, then we said if you get this one minus this one, you get this one. Also this one plus this one, you get this one. That's how you will get. So we called this one the absolute error. So this is in the case where you are just trying to find out what the possible error a person can get if they are trying to measure this one in theory. But in practical, if they do the measurement, and then they find that is in their measurement of 10, this is 10, sorry, then they get instead 10 point maybe 4. Then what we are saying is the absolute error in that case will be this measured value minus this. Then you get what is known as the absolute error. So now we are saying we also have another value that we deal with called the relative error and the percentage error. So we are saying the relative error is the ratio of the absolute error to the actual value. So if you get the actual value here divided by the absolute error, you get what is called the relative error. So we are saying relative error now is given by equals the actual, absolute value or error divided by the actual value. Then we have now percentage error. So percentage error is just equal to absolute value divided by actual value times 100%. So let's do some examples so that you understand. So example 3 says 1. The actual value of the length of a rectangle is 10 centimeters. If the measured length was recorded as 10.2 centimeters, find A, the absolute error, then B, the relative error, then C, the percentage error. 2. Find the relative error and percentage error of 7.2. Now solution. So now before we do solutions, I have put deliberately two type of questions, two different type of questions, but asking to solve almost the same thing in a different way. So the first one here is dealing with a person doing the actual measurement, and they're trying to measure the actual length of the triangle. By truth, it is supposed to be 10 centimeters, but in their measurement they get 10.2 centimeters. Then we can still find what we call the absolute error, as we showed. Absolute error is equal to measured value minus what we are calling the actual value. Then yeah, that's how it is. So this question number 1 is dealing with when a person does the actual measurement. Now when you look at question number 2, question number 2, we haven't been told that a person did the measurement and they got something. We are just told find the relative error and percentage error of 7.7. So this value here, now it means that if a person is to get this value closer to this, you find the lower limit they can reach to be closer to this, or the upper limit they can be away from this but closer to it, away but closer to it. So that is now theoretical for the person to be considered to be correct. All right, so we are going to start with number 1. So solutions for number 1. So for number 1A, we are saying we find the absolute error. So absolute error, we said, is equal to measured value minus the actual value. Then this should be in modulus. Even when I didn't put in modulus, sorry, this one should be in modulus like this. Then which will be equal to measured value here is 10 centimeters, then minus the actual value is 10.2, then the actual is 10. Then we'll put modulus, then we'll say centimeters. Then when we subtract these, we'll get 0.2 centimeters as the absolute error. So when you check here, this absolute error in the measurement, this is how it should be. But if you were to do it theoretically, where a person did not measure, it would be 0.5 centimeters. And I've already shown how to find this one. All right, so now let's move to B, where they're asking us to find the relative error. So we said the relative error is equal to absolute error divided by actual error, which will be equal to absolute error, we have found it 0.2 centimeters, over the actual value is actually the one we put here, which is 10, which is 10, this one here. All right, so let's push it this way. So say relative error now is going to be, we divide 0.2 centimeters by 10, which will be 0.02. It will have no units because these will cancel each other. All right, so if we go now to the percentage error, so say let's move for percentage error C. So we are saying percentage error will be equal to absolute error divided by actual value times 100%, which will be absolute percentage error equal to absolute error, we found it to be 0.02, then actual value is still 10, then we'll say times 100%, then absolute percentage error will be equal to, when we divide this by that times 100, we'll get 2%. All right, now let's move to question number 2. So I said question number 2, first we'll do the list. So the list value of 7.7, it will be actually 0.1 because there is one decimal place in this one. So now we'll say the list unit is 0.1. So then absolute error now will be equal to half of this one, which will be 0.05. So this will be an absolute error. So now to find now the relative error is going to be equal to, we said absolute error divided by actual value. So we'll say equals absolute error, which is 0.05, then over actual value will be 7.7. Then when we divide, we'll get 0.006. All right, so now we are done with this part here. Now we can deal with this part here. So say percentage error is going to be, now you'll see that percentage error is only found by just multiplying by 10 to the same relative value. That's what by 100% I mean. So now since we already found this here, which is this, so it is as good as just ignoring. So anyway, we'll say that is the case I'm talking about. Then times what? 100%. That's what I'm saying. So now equals, so we find this one, it is this, and we found this value. So we have already found here, this part here, it will give us 0.06 times what? 10, 100%. When we multiply this, we'll get the percentage error as 0.6%. So yeah, we have come to the end of this mathematics lesson. So I'll be able to share with you some examples or some questions that you'll be able to practice to answer this, to be able to answer this question when it comes in the exam. As for now, bye and see you in the next lesson.